This is the next set of lectures, following on from the ones you've had so far. So just looking at the schedule, there was intro ones from Mike, then there was all the basic EM relativity from Jonathan and Chris. Now we have 6 lectures with me on beam dynamics, and I made it as basic as possible to start everybody off, and also it goes quite broad towards the end, seeing a survey and everything. So we have 6 lectures, and then Neil comes in with magnets, and then Graham on RF. There's one small change. In the first version of this, there was no lectures in 2 weeks' time, and there was lectures in 2 weeks' time, and there was no lecture next week. Now it's changed, so that lectures 3 and 4 for this will be next week on the 3rd, and the break will now be the 10th of November, which was different to the first schedule. So what we're going to do is the ultra basics. So we'll go through and we'll do the ultra basic. We'll derive pretty much everything, which I think is important for when you first come across all this kind of stuff. We'll look at introduction, basic information about accelerators and how we describe beams, then different approaches to doing dynamics, so Newton's and Hamilton, not Lagrange. We don't need Lagrange, we need Hamilton and we need Newton. Then we'll derive something called Hill's equations, which are the basic equations, linearized equations for motion of a particle in an accelerator. And we'll derive them, and then because they're linear, we'll write them as matrices. Then we'll use the properties of linear algebra to extract global information out of our accelerator, our storage ring. Then we'll go on to something called the Cohen-Snyder formalism, which is how we normally do lattice design, optics, and beam dynamics, and look at things like stability and tune. Then we'll have a bit on a lecture or so on optics and lattice design, basic building blocks of any accelerator, how to design an accelerator, how to design a collider, mini beta. Then we look at generic optical structures. Then I'll throw in a few slides on real structures that have been designed in the last couple of years, so it's a bit more contemporary. Then we look at what happens in real accelerators. We have errors in our lattice. We build a magnet, it's not quite perfect. We look what happens in the beam dynamics. Then we come on to something called real particles, where we look at particles that are not on the ideal design momentum, and to compaction, chromaticity, and then the topic of emittance, which is the volume occupied by a beam in 6-dimensional phase space. Then we have a bit on longitudinal dynamics, which will be much quicker, but it will bring that part of the motion in line with the transverse part. And I'll explain why there's 6 bits for transverse and only 1 bit for longitudinal. That's very important. And then there's a part 8, which we probably won't have time to reach, but the slides will be there. And it's mostly directed reading on radiation effects, synchrotron radiation, and what happens in storage rings to the emittance over many turns. So that's what we'll do. I don't know if anyone's talked to you about books and other course material, because there's loads out there now for accelerators, both for us, for the Cockcroft. So on the left column, if you go to the education page, there's now about 8 years or 9 years worth of Cockcroft courses, both internal speakers but also external speakers on a whole variety of subjects. All the slides are there, most are videoed. So you've got like a trip on a plane or something, it's a great chance to go back and watch some lectures on, say, spin dynamics or something like this, and they're all there. And there's also the CAS schools, the USPAS schools, these global international schools of accelerator physics to go to as well. There's lots of material available. And there's books as well. There's millions of books in this subject. There's about 10 or so basic books on accelerator physics. I've listed some of the better ones there. Lee is probably my favourite. Weidemann, it's a big, thick, fat book covering most of the subject, way beyond all the courses you have in the Cockcroft. Villa, which is quite a good introductory book. I give this to undergraduates, when they do like 4th-year projects and things like that. That's a very accessible book on beam dynamics. Foray, that's probably the hardest book we have, very formal structure, mathematical structure, beam dynamics. The best book for longitudinal stuff is probably Wangler, which is a book dedicated to longitudinal dynamics and accelerators. That's probably the best one of the lot, and there are loads more. You can buy them all off Amazon. Also, Andy Walski has just brought out his book on beam dynamics, which is very good and based directly on his Cockcroft lectures. So that's another good book to have. So there's loads of good books. It's worth having one as a reference, and they all have different notation. That's a problem with our subjects, and has all have different notation. So it's good to pick one textbook and then follow it. I use notation mostly of Lee, because that's quite good, solid, quite theoretical, but it's very rigorous. So that's the notation I tend to use. So what we're going to do is, this is kind of the pathway to being an accelerator physicist. You have to start off with all the basic stuff, special relativity, You know this from your previous education. Maxwell's equations, which is our bread and butter of magnetism, and also classical mechanics. You know this kind of stuff. You then combine it into studying the motion of charged particles and accelerators, both transversely, longitudinally, at high beta, at low beta. And what we tend to do in the subject is split it, and I'll explain why as we go on, into transverse beam dynamics and longitudinal beam dynamics. In fact, that's a rather arbitrary split. I mean, after all, a particle lives in six-dimensional phase space, so why would you have this arbitrary split? But it turns out that in strong force and accelerators, we have lots of oscillations transversely in one loop of the accelerator and not so many longitudinally. So the motion is slightly different in how we approach it as a result. Some courses, probably my preference as well, is not to have this split and do everything together using Hamiltonians. But that's not very accessible. You tend to lose some of the insight by doing that. So traditionally in accelerator physics, you have a course like this one that uses Newton's dynamics and does this first and treats that separately. But when you do it more sophisticated, you go back to Hamiltonians, we drive everything and do these things essentially almost at the same time. That's probably a better approach. But we're going to do things traditionally here because that gives you much quicker insight to what's going on and you understand what things like a beta function really start to mean. Then once you've done all this stuff, you go on to more specialist stuff, which you'll do some of these in the Cockcroft courses, RF design, how to design cavities, collective effects, space charge, beam-beam interactions, magnet design. Neil will do this on the series of lectures, optical design, linear dynamics, operations, and many, many more. So we'll have at the Cockcroft loads of specialist courses. You kind of pick this stuff up when you go and do a job, be it a PhD or a postdoc or whatever. You pick this stuff up as you go along, because you can't learn to design a lattice in a lecture theatre. You don't do that. You do it actually doing it. So you pick this stuff up as you go along, but it all rests on understanding the basic dynamics. So the first part is introduction. I'll go fairly quick on this because we've lost a bit of time. And what we're going to study really is storage rings, because they're the typical accelerator that you have to deal with. Diamond, or the LHC, is a storage ring. Normally these things are pretty small, so we're going to start with the largest storage ring that we can see easily, and that's the solar system. We do this for two reasons. One, if you look at this, you have these big planets going in nice stable orbits. What's nice is if you look at these planets and wait a year and 2 years, they're still going in nice stable orbits with very predictable properties. So the fact that this is a stable storage ring is actually a non-trivial statement, and we'll look at this in the concept of accelerators. The second reason why we're interested in this is the guy called Hill, whose Hill's equations we spend most of our time deriving today, was actually interested in astronomy and planets. And he derived his equation, Hill's equations, in the context not of accelerators, but in the context of a planet in a stable orbit around the sun, in the same way protons in the LHC are in stable orbits at every turn around the accelerator. So in some sense, this is a storage ring, and this is the kind of thing we're going to be studying in detail. We'll also, hopefully, think back to undergraduate education, we're going to be interested in pendulums quite a lot, and you'll see why as time goes on. In a nutshell, particles and accelerators oscillate transversely and longitudinally, and the equations look pretty much, for a linearized case, like a pendulum equation, which is kind of cool because this is easy to solve, dead easy to solve. If you think back to your undergraduate education, probably first year if you did physics, we did a course on vibrations and waves in Manchester. That's what we have, course on vibrations and waves. We have some pendulum described by some coordinate, be it the angle or displacement or something like this, and it has some return force. It could be a torque, or it could be a force from gravity in the case of the pendulum. And if you write down the equations, you have a return force. You can have this coordinate u written as this kind of differential equation here, which is the simplest kind of differential equation you can have. You can solve that by inspection. That's oscillatory solutions, sines and cosines. So you do that in first year at university. And that is the equation of this pendulum. It's also the equation of a particle in an accelerator, which is kind of good. So also we see periodic oscillations which go on forever in the absence of damping. So also the motion is stable. The only difference for us in an accelerator, the return force bringing it back to the centre, is not arising from gravity. It arises from the action of our magnets, our quadrupoles and our sextupoles, that we do to define the motion of the proton or the electron through the accelerator. So you should be able also, if you just flip that sign to a negative sign, solve that fairly quickly in your head as well. You get diverging solutions then in terms of Sinchus and Cauchys. Think back to your undergraduate education, that's what happens. So you can just check by substitution or some other fancier method. But this equation will come up time and time again. We'll solve it explicitly, so don't worry if you haven't seen it. So there's a synchrotron. This is what we're going to try to understand the dynamics of. Turns out it's just like a pendulum. The transverse motion of a particle going around this accelerator is just like a bob of a pendulum. It oscillates around some equilibrium position. The oscillations are governed by quadrupole magnets. You can just see one there, 1, 2, 3, 4 poles, but it oscillates around some equilibrium path, and that's defined by the dipoles, the constant field bending magnets. And you can see them here. There's 2 poles there, and what these do is define a curved path around the accelerator about which a particle will oscillate. And that's what's going to happen in our analysis. We'll define some kind of reference trajectory, which will be defined by where the dipoles are, and then we'll have particles oscillating about that trajectory through the accelerator many, many times. Then by using linear algebra, we'll demonstrate that this motion is stable for many, many turns of the accelerator. That's what's going to happen. Here's another synchrotron. It's a circular accelerator called Diamond down at Row in Oxfordshire. You can see there the very characteristic circular design, again defined by the dipoles of which particles oscillate around. So that's quite a nice aerial picture. Now, just as a fun game, this is probably the easiest bit of the lecture. Imagine you were an alien and you came to Earth and you looked at Diamond. You know, what observations do you make as a mathematical physicist, as a physicist, an engineer, and what would impress you? You know, I won't say that as a tutorial question. You know, it's something to think about, but actually the answer is quite amazing when you think about it. That if you look at, say, Diamond or the LHC, and we'll look at some real data in a sec to back this up, particles spend a long time in the ring. You know, the motion is stable. So the fact that these little guys are bunches or tens of microns across, and the thing is 100 meters across, they go around many, many times a second, they do that for 10 hours in a tiny little cross-sectional space, oscillating away happily with different motion every turn, but the motion is stable. That's pretty amazing when you think about it. And so we look at the LHC and think about hard numbers, and that even gets more incredible. I think once you start to do maybe the Cockcroft lectures and reach the point where you think, how the hell do accelerators ever work at all, you start to understand a little bit about the complexity of the dynamics inside these machines. The motions also, the machine rather is periodic. So imagine you had a video camera glued to the top of an electron going around Diamond. Every turn you made, you'd see the same arrangement on magnets. And you might even see the same arrangement of magnets on a shorter time scale when you have periodicity inside of one turn. You have repeating cells of magnetic structure. So the machine is periodic. Then, next one's probably harder to guess, but the motion of a given particle does not have the same periodicity as the machine on a particle-by-particle basis, but the envelope or the maximum oscillation size around the machine does indeed follow the machine periodicity. So the first one you can probably guess, the other two you probably won't, hard to get your head around, but what we'll do is these are observations. Essentially our goal is to understand why this is the case. Why does Diamond work? And we'll explain and derive all of these using beam dynamics. There's also one more I'll add, which is an observation you would make, and in a more advanced course you'll study. You have symplectic motion in hadron machines and nearly symplectic in electron machines, and I'll define that term in a couple of weeks' time. But that's a very important feature of our equations. They have loads of properties, and a very important property for us is symplecticity, and I'll define that as we go on. So let's back all that up with the LHC. Let's look at some numbers to convince you what I say is true. There's the LHC. It's the proton synchrotron on the border of Switzerland and France. There's Geneva Airport, in case you haven't seen this picture before, but I'm sure you have nowadays, the Higgs and everything. It's very prevalent in scientific talks. There's Geneva Airport, to give you a sense of scale. That runway can take an A380, so you get a size of the scale of the LHC. That's one proton synchrotron, and that's the main LHC ring, which is a 27-kilometre proton synchrotron. So what we essentially do is we stick particles into that, and they go round and round. So some of the parameters of the LHC, just to give you an idea of what we're dealing with. Our equations describe a lab across over there, but also describe what happens in the LHC. So LHC is just give you a normalization for synchrotron parameters. We have a beam energy of 7 tera-electron volts per beam. Think back to your course of relativity, you should know what those units mean and how to handle them. We have particles accelerators come in bunches. I'll explain why. We'll derive that fact as the course goes on. And we have 10 to the 11 protons per bunch. So quite a lot, 100 billion protons per bunch. We need that because we're doing very processes that generate very rare particles like the Higgs boson. So we need lots of protons in there. We have almost 3,000 bunches per beam. So there's a lot of protons in the LHC, 10 to the 14 protons in the LHC. And it means that the maximum stored energy, well, the stored energy per beam for these parameters is almost 400 megajoules in something the cross size of 100 microns. So we have a lot of energy stored in our accelerator. We have a beam size where the bunches collide of 16 microns. So we squeeze that energy into a size of 16 microns. So synchrotrons are pretty impressive machines. And a parameter that comes relevant later on, the bunch length is the order of 7.5 centimeters. So if you look at the LHC and you put lots of little devices that measure the position of a beam transversely. So this is essentially the position of the middle of the bunch of protons as a function of position around the LHC, as a function of a position, horizontal and vertical. So that's horizontal position in millimeters, vertical position in millimeters. You see what happens is this bunch of protons is moving up and down around the machine horizontally. A typical excursion is the order of a few millimeters, and you can see a very well-defined oscillation of this beam position around the LHC. So you can see it from the BPMs, and you can see in the vertical plane it's slightly more complicated, but we still have this well-defined oscillation around the machine. So the statement is there's a closed design orbit around the ring, which is not 0, 0 everywhere, it actually oscillates, and all the particles in the bunch oscillate around this design orbit. Now this is the design orbit because this measures the average transverse charge distribution of the bunch. So that's the middle of the bunch, if you like. So at a given point in the LHC, that's the middle of the bunch, and everything else oscillates around that middle. So this defines what's called the closed orbit. And you can see, if you look there, it is closed. It's coming back on itself at the same angle and the same position. And the dipoles generate this closed orbit, and the quadrupoles, we're going to look at focus the beam around this closed orbit. Also pretty cool, here is a picture of the intensity, the number of stored protons in the LHC as a function of time. Blue is beam 1, clockwise beam, and red is beam 2, anti-clockwise beam. See, that's where this is the number of protons stored. So we put protons in the machine at 4 p.m. on the 4th of April, and they stay in the machine until 2 p.m. on the 5th of April, 24 hours. So that's hundreds of megajoules, cross-section size 100 microns, oscillating around a beam pipe of a few centimeters across for 24 hours. So synchrotrons are pretty amazing things. Trying to steer this beam once through one turn is very hard. Once you've done it, they have a closed orbit, it can stay for a long amount of time. So synchrotrons are pretty amazing things. The black, by the way, is the energy. So what happens is we inject the LHC in low energy, then once we're fully stored the beams, we then ramp the energy, the top energy, with the beams stored in the machine. That's what happens. That's how the LHC cycle works. So beam lifetime is pretty amazing. Here's HERA. So HERA, you've not heard of it, is an electron-proton collider that was in DESY in Hamburg. It's shut down now, where we have a proton beam at almost a TeV, and here in this case a positron beam at 28 GeV, and here we have the lifetime, and you can see this is the stored current as a function of time in hours, and you can see again proton beam, electron beam are stored for a much longer period. Note, by the way, the decay of the electron beam is bigger than the decay of the proton beam, and we'll understand that as the course goes on. So see, the lifetime is very important. So that's a few observations about beam dynamics. So what is beam dynamics? That's what we do. A lot of us in this building do with our time. We understand the motion of particles in linear and circular accelerators for loads of reasons. One, it's our job, or it's our PhD. Another one is to understand how existing machines work, optimize and commission new accelerators, design new machines like a new collider, that's what I spend my time doing, or designing novel machines like a non-scaling FFAG like Emma across the road. And how do we do this? Well, the tool of a person doing, in quotes, beam dynamics is knowing how to calculate the motion of a charged particle in a real electromagnetic field. That's what you're doing in all these situations. We store charged particles because they have a charge, they obey the Lorentz Force Law, and we have equations that tell you what these particles do. A lot of the time, these calculations are wrapped up inside of codes. You know, people in this building use codes, but these codes are just doing what we're going to discuss in this course. And it's very important to use these codes to actually understand what they do. So you have time-dependent fields, static magnets, doing optics, and we'll do optics as this course goes on. What are the approximations used? Very important. For example, in FFAG, you often violate the approximations in most textbooks. You have to understand the approximations before you violate them. How do particles interact with their surroundings? Wake fields, collective effects. Do particles in a bunch interact with themselves? That's called space charge. We won't discuss that, but there are lectures on space charge later on. So this basic question is, I've got an accelerator, how do I represent mathematically a charged particle beam? What do I do? Well, there's loads of ways of doing it, and I'll try and explain why we have different approaches, and textbooks are really thick by thinking about gas. Right, this is, again, basic physics. I presume you've all come across the ideal gas law and statistical mechanics and things like that. So think of a box of gas, there, a bunch of molecules in some kind of box. We can describe this gas by a small number of numbers: its pressure, its temperature, and its volume, macroscopic variables. And there are a very limited number of them. It could be 10 to the 23 molecules in that box, but there's only one pressure. And an equation of state will relate these quantities together. For example, the ideal gas law, PV equals nRT, relates these variables to each other, these macroscopic variables, and tell you how they change in different situations. So we have the pressure of a gas, but also a gas is made up of a whole load of individual molecules, 10 to the 23, some vast number. Each of those has a position and a momentum, so 6 degrees of freedom. So we can also think of a gas as the speed and position of that molecule, of that molecule, of that molecule, of that molecule, and this is a microscopic view of a gas, and it's equally valid, but somehow this view in terms of individual gas molecules is related to the macroscopic view in terms of the pressure, the temperature, and such things. So you have a dual description of a gas, look at individual molecules, or pressure, volume, temperature, and such things. It's like a dual description. And these things are related. For example, K is 3/2 nRT from basic thermodynamics. So we have these two descriptions, and is it a genius to see what I'm about to say is that in an accelerator we have exactly the same situation. We have 10 to the 11 protons in an LHC bunch, each with a position and a momentum. So you can think of it on a particle by particle basis, or we can try and do some kind of zoomed out approach and have macroscopic variables that describe an entire bunch of particles. That's what an admittance is, that's what a beta function is, and that's what we'll do in this course. We'll have these two different descriptions. But there's definitely a relationship between them. So it's common in physics to have different views, but equivalent views of the same situation. Physics and ideal gas, quantum mechanics, the wave and matrix formulations. We have the same situation in beam dynamics, and we have this dual approach. There's a global view where we assume some ring or beamline exists and study its global properties. Things like, is a ring stable? Yes or no? It's a global property of the system. Or calculate something called a tune, which is a property of a ring as a whole. And we'll do that. And we'll derive the current Snyder formalism to do that. Or we'll have a local view, the details of the machine. What frame of reference do we have to define our particles? What do the fields look like in that frame? How do I stitch together the frames of many magnets? And how do single particles move in this system? And also, do they interact with each other? So we have this dual view to worry about, and we'll advance both as time goes on. So first of all, we have to do dynamics, and this is our fundamental first decision as a beam dynamicist, a fledgling beam dynamicist. So we have to do dynamics. Do we have forces? Do we have Hamiltonians? What do we have? And I don't know your backgrounds, but what I'll do is I'll give an introduction to those different methods. If you're very theoretical, then good, you've seen it before. If you're not, don't worry, I'll derive everything we need. Ultimately, I'll be following the standard way of the subject and using forces to do everything. But I want to just point out you can do things in different ways because future courses will actually do that. So if you're back at school, there's three formulation dynamics: Newtonian dynamics, forces, Lagrangian dynamics using Lagrangian and Lagrange equations, or as Hamiltonian dynamics using a Hamiltonian-Hamilton's equations. And typically in a physics degree, you do this in the first year, use forces, then years 2, 3 onwards, you understand about Lagrangians and Hamiltonians, and you write this down and find it's a much better way of doing dynamics for reasons which I'll tell you about as time goes on. But really the message is, once you're familiar with them all, what you choose depends on the problem you're solving. And in accelerators, we tend to use Newtonian at first and Hamiltonian dynamics later on, and each has its own merits. So let's look at them in turn. So Newton, there's Newton there, a very clever chap. His formulation of dynamics is all to do with the force, and doing physics, if you like, is a getting this force. And once you've got the force, you use Newton's second law to figure out the motion. So there's the force, and generally depends on the position dotted, or the velocity and the time. And once you've got the force, you can use Newton's second law, d by dt of mx dot, to calculate the resulting motion. That's what we're going to do. That's the good way of doing it. So a physicist's job is to define a coordinate system and then figure out the force, which depends in general on all these different things. Then we solve Newton's second law to get the position and velocity as a function of independent variable time. Because this time here is kind of different to this x and this x dot. This is the independent variable, and x and x dot depend on time. So I made a formal structure there in what we're doing. So here's a good example. First example ever at university normally is a mass on a spring. There's one. And if I just pull that and pull it down, it oscillates up and down with a restoring force coming from the compression and the extension of the string. So some equilibrium length, it just sits there. There's some spring constant k, some mass m. If I just pull it down by y0, there's a restoring force on the string being stretched, pulling it back up and oscillates up and down. And Hooke's law says that the restoring force is equal to minus the string constant times x, the displacement. Okay, x and y0 are the same there. I should change that slide. That x is the distance from equilibrium, and that gives you a restoring force. That's called the return force in dynamics. And if you have, so there, we've just done physics, we've found the force, now we just hit with Newton's second law to calculate the resulting motion. So if we do that, the force is given by minus kx, where x is the displacement from equilibrium position. For us, if that's a closed orbit in the accelerator, by the way. We then use Newton's law, that's the force, that's Newton's law, to get this equation of motion, which you should have seen many times before, and I hope you have. If you haven't seen an equation like that before, then pay attention when I talk about it, because that's of central importance to what we're doing. Now that's a very, very simple second order linear ODE. We can solve that very easily by all kinds of methods, but the best way is our physical intuition. Our physical intuition just says it's oscillatory with some frequency of oscillation. So we guess at this solution where that's an unknown constant, that's an unknown constant, substitute that back in, and you'll find this does indeed be the differential equation if omega squared is given by the ratio of the spring constant to the mass. You should have seen that before back in your physics or engineering degree, so that's good. So we've written down the differential equation, we've understood how the spring moves. This has two unknown constants, x0 and phi0, which also we can just write. So we can write the whole solution in a different form. There's sine omega t plus cos omega t, and the constants have become c1 and c2. And it's a well good first year problem in tutorial number 1 to relate c1 and c2 to x0 and phi0. That's dead easy. Which means we can just write the equations of motion as that, as an aside. So what we've done is we've found the force, we've found the motion, and we've found its oscillatory. As an aside, imagine if the force was not given by Hooke's law, minus kx, but given by the opposite sign. So the restoring force was no longer a restoring force. The force is now given by some constant times x from the distance equilibrium. So as x gets really big, d squared x by dt squared also gets really big. It accelerates to even larger x, so you get diverging solutions. That's our intuition. So our equation of motion is now this, which you can then find by substitution is solved by a linear combination of coshs and sinches, or e to the omega t and e to the minus omega t, diverging solutions. So the sign of this guy here determines whether we have oscillatory solutions or divergent solutions. I know you've probably seen that before. I'm saying it again because these are the exact equations we'll have in a quadrupole of the two different polarities, a focusing quadrupole or a defocusing quadrupole. So that's why I've gone through that very carefully. And a very important equation for us is the Lorentz Force Law. There's Lorentz, the guy. This relates the force on the particle of charge Q for external electric and magnetic fields. You should have seen this before. If you haven't, tell me at the break, but I'm sure you will have. Where if we have some external B field, some external electric field, the force on the particle is given by Q electric field plus Q times the cross product of the velocity and the magnetic field. Good standard electromagnetism, good old first year stuff. So notice I've written this as a vector equation. This is very important and should have been covered in your course electromagnetism you just had. Was that right? Has it? Good. I'll take that as a yes. Now, A and B, of course, are B equations, which specify the vector fields in the presence of sources and boundary conditions. That would be the job of the magnet course to do that. So we're going to always assume A and B are given, and we look at the consequences on the motion using this equation. Other courses will find the E's and the B's using like magnet design or something like this. And also, here's a caveat, usually the speed is close to the speed of light, and I'll show very shortly that's why we use magnets to guide particles, because generally particles go at the speed of light in a storage ring, but not always. We'll derive the case mostly of ultra-relativistic particles because that's the most common case you find. Just be careful in other situations where they're not relativistic, because then you have problems. Just a word on Hamiltonian mechanics. There's Hamilton. There's also formulation by this chap. This has a great advantage, which I find really, really useful, of a really well-defined mathematical framework. So keeping control of variables, invariants and approximations is much, much easier. You'll see after coffee what we're going to do is make loads of approximations. It's a bit uncontrolled at times, the impact of these. In this kind of framework, you really understand what you're doing, what your variables are, what your approximations are, and you have all kinds of access to a lot of theoretical machinery. So this is quite good. So essential importance in this framework is a thing called the Hamiltonian, which plays the role of the force, which is a function of a set of pairs of conjugate variables. So for example, in one dimension, we have the position, and conjugate to position is momentum. So this forms a pair of variables, and the Hamiltonian is then a function of these pair of variables. So in 3 dimensions, in 3-dimensional space, we have 6 variables, spaced in position and momentum in 3 different planes. So once you've got the Hamiltonian, you then use Hamilton's equations to figure out the dynamics. That's like Newton's second law in Hamilton language, where dx by dt is given by partial dh by d momentum, and dp by dt is minus d Hamiltonian by d position. If you've seen those before and you're happy with them, great, we won't use them. If you haven't, don't worry, we're not going to use them. But I want to point out that in future courses you will be using them, but it's a nicer approach. So what this gives you is a set of 2n dimensions, first order ODEs, which are easy to solve. We'll have a 1 second order ODE, which is unpleasant in normally any kind of analysis. You would change that to 2 first order ODEs if you do this straight away. So the Hamiltonian is playing the role of the force does, and conventionally our subject is arranged that students of the subject will learn the way with Newton first and of Hamilton second. If that's right or not is debatable. However, what we've done for this course is we've adopted this conventional approach of using forces because you get intuition coming out very, very quickly. So we'll do an example of how you do it for the oscillator. The Hamiltonian for an oscillator is this. This is just kinetic energy, p squared over 2m, plus some potential, which is quadratic in the position variable. It doesn't matter where it comes from. You haven't seen it before. If you have, you know how it works. So that's the force. That's Hooke's law, essentially. Now we apply Hamilton's equations to derive 2 first order ODEs. This one essentially is telling you how the momentum relates to velocity, And this one is your real equation of motion, which we'll now go ahead and solve. And also note the Hamiltonian, as an aside, can be written as two terms, a potential part and a kinetic part. That's the origin of the Hamiltonian in the subject. So as an aside of why we love Hamiltonians so much, if we take the total time derivative of our Hamiltonian, which depends on x, px, and t, so there's three variables inside of h, so d by dt, the Hamiltonian has three terms, partially h by dx, dx by dt, it totally depends on momentum, and also the explicit dependence of the Hamiltonian on time, partial dh by dt. We can then rewrite this using Hamilton's equations. Don't worry about the algebra, just look at the structure of what we're doing. Then this term cancels with this term, and we get that the total time derivative of time of the Hamiltonian is just given by dh by dt partial. So if the Hamiltonian is not explicitly time dependent, then it's a conserved quantity of the system. So whatever motion my particle does in the LHC, the value of the Hamiltonian at any point in the accelerator is always the same. It's an invariant, and we love invariants in theoretical physics. So this is why we like this approach, and this is very, very powerful. And you'll study this in other courses. But this is just an aside of when people talk about Hamiltonians, why they love it. The Hamiltonian for us in an accelerator is a conserved quantity, and that's cool. So there's Hill's equations. So we've seen harmonic oscillator equation with different signs can lead to oscillating and diverging solutions. We've seen that from a pendulum, we know that. What we're going to do after coffee is derive these guys, which are the basic equations of motion for an accelerator, linearized, transverse, and they're called Hill's equations. And we'll derive these after coffee. So that's the motion in the horizontal plane, and that's the motion in the vertical plane. Notice it looks like the pendulum equations. You've got a second order derivative, you've got the variable there, then you've got this constant that sits in front of the second term. So depending on the sign of this constant, we're going to have oscillating motion or diverging unfocused motion. What's going to happen is that k is going to come from our quadrupoles and our lattice, and this 1 over rho squared will come from the natural focusing of dipoles. That's what's going to happen. And in the vertical plane, there's no dipole natural focusing because we don't bend in that plane, we bend in the horizontal plane, so we only have a term coming from the quadrupole. So we're going to derive these guys after coffee. We'll take the second one, equations of motion for a region with no bending. So I can choose k to be positive or negative, so by choosing different quadrupoles, I can have focusing in the vertical plane or defocusing as I choose to have in my accelerator. So an accelerator is built of regions of differing signs of k, giving us, hopefully, oscillating motion in both planes. And that's what's going to happen. We can achieve that. So I've just shown them to you, but what we have to understand is we'll derive them after tea, after coffee, but it's really just the pendulum equations. So the solution for them, for us, is now trivial. We know what's going on. And if you look at these basic accelerator codes, the linear motion is just a whole bunch of sines, cosines, sinus, and coshs. So you can think of an accelerator, at least linearly, approximation made there, as being made up of piecewise regions with different sizes and signs of the spring constant. So an accelerator is just basically a bunch of regions where we have different values of some spring constant acting on some particle. That's all it is. That's all it really is. So we give k an argument of s, and we give rho an argument of s. We arrange dipoles, we arrange quadrupoles, a function of position, and when the particle goes into a given region, we know the equation of motion has to obey. So this is a very, very good analogy. So this k, this variable, is our spring constant. We called it k for that exact reason. So that's a quadrupole. You'll learn about the motion in this course, and you'll design them in Neil's course afterwards. And that's got 4 poles. It gives a linearly restoring force, just like Hooke's law on our particle. So that's the equation for a particle in a linearly restoring force in a pendulum. It's also the equation for a particle in a quadrupole, because it's the same. So where we have some kind of, this is the B field lines, as you get further and further away along this axis, you get a linearly increasing force pushing you back towards the middle. So the motion of our pendulum is oscillatory, and the motion transversely of a particle through that quadrupole is also oscillatory. I know I'm banging on this loads of times, but this really is the point of what we're trying to do. So what's the basic idea of accelerator physics? We're going to use magnetic and electric fields to accelerate and control the particles inside the accelerator. So somebody will design a magnet in an accelerating cavity, give you the E field and the B field. We'll then use this equation and Newton's second law to calculate the motion and design the accelerator. That's the basic idea. We'll use the B field to deflect particles. We don't build the dipoles of the LHC or a diamond out of electric fields pointing transversely, because we can use a magnetic field and really benefit from the presence of the velocity in the Lorentz Force Law. So imagine we had a field of 1 Tesla. That's a nice normal conducting magnet. You can buy that, not so expensive. The magnetic force of a particle of velocity c and charge q can be written as the charge times the velocity times the field. And I've written Tesla as volts seconds over meters squared, which you should get from your electromagnetism course. So you just cancel out your units, you'll find that the force on a particle from this 1 Tesla field is the charge times 300 units of megavolts per meter. So the 1 Tesla field from a magnet actually has given us an equivalent bending force we would get from a 300 megavolt per meter electric field. And that, making fields of 1 megavolt per meter is very, very hard. So 300 megavolts per meter is very, very difficult. So deflecting particles with a magnetic field is really efficient because of the presence of the velocity in the Lorentz Force Law. So in accelerators, we normally use B fields to deflect, guide, focus, and correct, because it's very efficient. But we also use electric fields to accelerate the particles. So we use RF cavities for that. And that's a question for you, is if this is so efficient, why can't we accelerate the particles using magnetic fields as well? Surely that velocity would help as well, and we can't do that. And I'll leave that as a question for you to puzzle over. We can talk about it in the tutorial if you can't figure it out. That's but just dynamics, essentially. So what do we do? We have an accelerator. We want to imagine this is the synchrotron like the LHC or diamond. We want to make our particles move in a circle because it moves in a ring. So we apply a constant magnetic field. So here's our coordinate system we'll always use. Z is pointing up, S is pointing along, and X is pointing out. You have some particle at some position in the accelerator, a radius rho away from the center. We apply a constant B field on that. And because it's at right angles to the motion, which is along the circle, the force is given by Q times the velocity of the particle times the magnitude of the B field. That's A level, I think, for me, circular motion. So we equate this to centripetal force. This is how we find the motion. Gamma mv squared over rho, because it's going at a radius of rho. And equate these things together, cancel a couple of terms. Notice that gamma mv is just the momentum of the particle. That's in relativity. And we find this very, very fundamental equation that the product of the bending field and the bending radius is given by the momentum of the particle divided by q. And that's a very, very, very fundamental equation in accelerator physics. What it does, it says, if I give you some strength of bending field B and a certain momentum of particle, it tells you what radius they adopt, or other way around, if I want a certain radius for a certain momentum particle, it tells you what strength B field I need to achieve that. So that's very important for us. So it's written up again there. So what it says is that a particle with momentum P and charge Q in a guide field B will follow a circular path of radius rho. This equation is so important, there's like 10 slides on it. So we're going to go over it lots. Or the product of the field and the radius a particle goes in is only a function of the particle momentum. That's pretty interesting. B field, probably an accelerator somehow. Rho, the complicated motion. But the product of B and rho, it only depends on the particle momentum. That's very useful. So the combination of P over Q is exactly that which we'll use a lot of times to normalize our physical quantities, for a reason you'll see shortly, and we call it something special. We call B rho, or P over Q, the beam rigidity. And this is used time and time again. You'll hear beam rigidity often be used. And what beam rigidity is, it's a way to normalize our equations so they're momentum energy independent. But note that the beam rigidity doesn't refer to specific radius or field strength. What B rho is, sometimes written in brackets, is thought of as a way of rewriting the beam momenta. So instead of beam momenta, we'll talk about beam rigidity, B rho, often in the brackets. But it's not talking about a B or a rho. It's shorthand for a certain way of formulating the beam momenta. And that's what we'll see time and time again. So here's an example. So B rho is P over Q. So 1 over rho, 1 over the bending radius, is given by the charge times the field divided by the momentum. So what happens in a dipole? Well, let's take a dipole of the LHC. The dipole, the LHC, has a B field of 8.3 Tesla at the design, nominal. The design momentum of the LHC is 7,000 GeV over C. There are units of momentum in this field. So what's 1 over rho? So I put this calculation here. There's the B field in units of volt-seconds over meters squared. There is the momentum, EV over C. We then cancel out a few terms of the units, bring the C up to the top, 310 to the 8, cancel some more, and we find that the bending rate of the LHC is 410 to the minus 4 per meter. So the units are right. Rho is in meters, so 1 over rho must be per meter. So you can do calculations now. And below the terms, if you want to calculate in your head, okay, I've got this B field, this particle, what has it bended? How does it bend? And the units will get you. The units are confusing sometimes. There's lots of C's flying around, there's GV's flying around, there's all kinds of stuff. But just go back to basic examples like this, and you'll see how the units work. So beam rigidity is well important. For the cases normally encountered relativistic, so the rest energy can be discounted, and numerically energy and momentum are the same thing. So you can write the beam rigidity in this easy to remember equation. The B rho in Tesla meters is given by energy in electron volts divided by C in meters per second. Probably more usefully, write it as P naught in GV over C times 3.3 gives you the beam rigidity. So they're useful equations to have in your back pocket for just calculating on the train what the rigidity is of a given particle. So 1 over rho is given by this, that's just 1 over the speed of light, which is useful working with high energy accelerators where energy of the beam is normally in GeV. And one last point, we normalise field strength, the beam momenta, normally. We divide, for example, the gradient of a quadrupole by the rigidity, B rho, to get energy independent values. So we'll see a lot of stuff like this going on. Some B field divided by the rigidity is some normalized field strength. A lot of that will happen, and you'll see how this emerges from the equations. So here's a quadrupole. Here's a normal quadrupole. We have a linearly increasing field from the center of the magnet, and what we need is a field that obeys Maxwell's equations. There's no sources or currents or charges, so curl B is naught. So you find that the field inside a quadrupole looks like this, linearly increasing in x with a value equal to the z coordinate, and in z equal to the x coordinate, where g is some field strength. So that's our quadrupole field. So this is the guy here, and the field increases linearly as you go across. Notice, for example, in the horizontal direction, the field points vertically, which is what we express by these equations. So I'll skip that because of lack of time, but it's on the online notes, so you can see it. So, I mean, it was one mention on one slide. I won't mention this ever again, but a combined function magnet. What we're going to show is for stable motion, we need to provide not only bending fields, but also focusing fields, the quadrupoles, the gradient we need for stability. So we do that by, in this course, mostly by having separated function quadrupoles. But before they were invented, people created the gradient you need for stable motion, not by having explicit separate quadrupoles, but by tilting the poles of a dipole like this. And if you look very carefully, you can see that there's a component of B such that Bx is proportional to Y. So this actually, so the horizontal field in Bx gets bigger in proportion to Y. You get a growing Bx component. So you can create focusing structures by having a dipole and a quadrupole by tilting the pole face. has to be small for stable motion. And I mentioned that only because in Neil's course on magnets, he discusses this. I realised I didn't, so I had to mention the fact that a combined function magnet is you achieve it by tilting the pole faces. How are we getting on? So there's an exercise, not to do now, we'll probably do it in the tutorial. Imagine you built a proton storage ring, beam momentum of 20 TeV over C, with 17,000 bunches, with 10 to the 10 protons per bunch. So basic questions: what energy is stored in this machine per beam? If the circumference is 83 kilometers and the field is 6.6 Tesla, what fraction of the ring is filled with dipoles? That's using these equations. We'd like to build a high energy LHC with a beam momentum of 16 TeV over C. Why is that hard? And lastly, the LHC beam energy is 360 megajoules. Why could that be tricky? So there's some questions. We can discuss these in the tutorial, try and calculate them. So 2 more slides before I have a coffee. Our job now after coffee is to get the equations of motion in Accelerator in a really simple, easy to follow way. What we're going to do is this. We'll get the motion with respect to the design orbit from the dipoles. We'll then assume the deviation of the particle coordinates from its design orbit is small, so the horizontal motion from the design orbit is only a few millimeters, so we can linearize our equations of motion. So you can actually make an expansion of all quantities around the design orbit for small coordinates. And that's the thing that we're going to do. And so what this means is we take some arbitrary magnetic field, in this case a B sub z as a function of x. That's what we have in the quadrupole, for example. But, well, no, not really. I mean, this is an arbitrary B sub z as a function of x. In a quadrupole, it's linearly increasing, it's only one of the terms. But what we do, this is the arbitrary field, and we make a Taylor expansion about the design orbit, assuming that x equals 0. So a Taylor expansion of this guy is just a constant term, dBz by dx times x, d squared bz over dx squared times x squared, and so on and so forth. Right? If x is small, eventually we can start to chuck away some of these terms. We then normalize to the beam rigidity, so we divide through by the rigidity, P over E. So we just normalize each term appropriately. And then what we do is we then rewrite the terms on the right-hand side. So this multipole expansion, we get, for this term, this is just a bending radius from the guide dipoles, bz naught over the rigidity, which is just 1 over rho. We found that a few slides ago. We then have this term, we've got an x, which we leave, dBz by dx divided by A over P is the energy normalized quadrupole strength, the gradient divided by the rigidity, which we call K. And we go on and so forth. So we can normalize the next term, the sextupole term, the octupole term, and so on. So we have a multipole expansion of some general field as a dipole component, a quadrupole component, a sextupole component, so on and so forth. So what we'll do in beam dynamics for us is we'll cross out all of these terms and look at what happens when we only have these 2 terms left over. In future courses, you can bring these terms back and look at the impact. So we'll do this after coffee. But lastly, I've talked a lot about oscillations and motion. Can we understand simply why particles oscillate in accelerators? Actually, we can dead easily. Do you remember I showed you Hill's equations, and there was a term 1 over rho squared from the natural focusing of the dipole. So there is some focusing even without quadrupoles. So let's look at this simple example. Consider a fixed energy particle in a pure, all-pervading, constant dipole field going into the page in this case. So here we have black is our reference particle. It just goes round and round in the field according to our rigidity equation. That's fine. Now other particles of the same energy also do circular motion. It's the same B field and the same momentum. They have the same radius of curvature. But look at this guy here. Let's just push this thing horizontally, offset it by a small amount from the black, the reference. And so this reference particle goes around in a circle, happily. This one also goes around in a circle, happily. Same radius of curvature. But look, if you watch the red from the point of view of the black, at this point it's on the left. Then they cross, and now it's oscillated over to the other side. It's now on the right. So the red particle is oscillating around the reference trajectory. Do you see that? Do you see what's going on there? That's just weak focusing. So This red particle, from the point of view of the black particle, our reference, is executing a transverse oscillation. And it does one oscillation for one turn of the accelerator. So this oscillation is called a betatron oscillation, a transverse oscillation, and happens even without quadrupoles. It happens from natural geometry of just going around in a circle. The number of oscillations of this red around the black is 1 per turn. So the tune of that particle is 1. So that's what tune is, number of oscillations per turn around the reference. So that's quite neat. You can see what tune is and betatron oscillations are from a simple picture. But there are 6 dimensions in phase space. That's x. Let's offset the particle, not in x, but in the angle of x. Do the same game. Again, it's stable, and again, it oscillates. That's good. Now, let's look at longitudinal space, first of all. Let's make our test particle a slightly different energy. Actually, in this case, slightly less energy. C and B field, so it's going to have a bigger radius of curvature as it goes around one turn, and you can see eventually it gets around the same point again, so it's stable, it'll keep going, but it just has a different oscillation. Note that this longitudinally is not really oscillating very much. It actually takes several turns to do that. That's because of the weaker focusing. Displace it longitudinally in S. Again, it's stable, same B field, same P, it just goes around the same circle. It's stable, so it's stable in X prime, at the angle in X, stable in momentum, stable in longitudinal position. What about Y? Let's displace a particle by a small amount in Y. It just goes up, same P, same B, it just goes around the circle again, but again, it's stable. So that's quite nice. So this is really good, right? This is a constant B field. We've got a stable storage ring. This would go on for days. But let's just displace it by a small amount in Y prime. You can see what's going to happen. The red has a small vertical angle. It's going to get bigger. So every single turn, this red deviates away from the reference. It's no longer stored. So this particle accelerator with a constant B field shows betatron oscillations, but it's not stable vertically. It's